Wei-Chen Lin at Busan National University. He will give a talk about trouble with geodesics in black to white hole bouncing scenarios. Please.
Okay, thank you. First of all, I would like to thank the organizer and APCTP for their hospitality and the effort they put in this conference. And it's an honor and a pleasure to be able to attend the conference in person again. So today I'm going to talk about the work I collaborate with Professor Dr. Hong and Professor Donghan Yan about this title trouble with the geodesic in black to white hole bouncing scenario. So we hope that we can put this one on archive soon. Okay. Next page. Yes. Okay. So first, the outline of today's my talk. First, I will give you a very brief introduction about the background and the model we considered, and then we talk about the how we use the thin shell approximation to generalize the model, and then I will introduce the geodesic analysis and use this method. We find the corresponding energy shift and squeezing of the radial geodesic, and then talk about the problem because of those effects. And then in the end, I'll talk a little bit about the possible rescue. Okay. So one of the biggest questions in theoretical physics is the singularity inside a black hole. And so there are many different quantum gravity theory trying to solve this problem. And one of the strong candidates is the loop quantum gravity. So in this theory, the singularity usually is removed and replaced by a black hole phase followed by a white hole phase. So this is what we say black to white hole bouncing scenario. So this picture belongs to the category of regular black holes. So in this case, a singularity-free solution can be interpreted as a classical extension of space-time. But even from loop quantum gravity, there are different approaches. So they create different black to white hole bouncing scenario models. So in this work, what we consider actually is this BNN model. So this is constructed by Bendendorfer and Melee and Munch by them. So the overall picture is very similar to this one constructed by Ashtakar and his collaborator. So the bouncing surface is inside the event horizon. So black hole followed by a white hole. And so this is basically a cyclic model. So to the future, there are infinite many cycles, and there also are infinite many cycles in the past. So what's the differences is that in Ashitaka's model, all of the mass of the black holes and white holes are all the same. But in this BNN model, there is a mass amplification or the amplification relation, and can be formulated in this short equation. And by choosing beta, the beta value of this parameter is either 5/3 or 3/5. Based on their calculation, this is the way to have the quantum gravity effect trigger at a certain curvature scale. So, and this construction is actually very complicated. So, and how do we generalize this and to study the classical picture? One way is the most common way is to use the thin shell approximation. So basically we assume we do a cut and paste. We do a cut and paste procedure. And there's a thing, so we cut and paste a black hole solution and connected with the white hole solution here. And here is the thin shell, and the thin shell has to satisfy the Israel junction conditions. So there are two of them. The first one is the induced metric must be the same on both sides. And the second one is the shield and the metric around it has to satisfy Einstein equation. Basically, you can, the idea of those two junction condition is from here, those two ideas. So basically what we do is this is the usual Schwarzschild solution. And here we swap the position of R and T because we want to emphasize inside of the event horizon. The R is the temporal direction and T is the spatial direction. And F is the 1 minus 2m over R. And also here I choose plus is for the white hole and minus is for the black hole. Sorry, I didn't put a symbol on this picture. But this is because I choose the future direction as the direction of the surface. Okay, so this type of case cut and paste is actually was started by Donghan and his collaborator Rama, and in this work. So the overall methods is the same, and indeed even in this cut and paste with mass differences, we still can find the stable solution here. Means that indeed, if we assume like we tune the parameter. Oh, sorry. Okay. If we tune the parameters for the thin shield, even through fine tuning, a static and stable solution exists. So this means that the white hole and black hole are connected at a minimal radius. Okay, so this is the type of situation we consider. So what's then? So if this cut and paste works, so what we can say more about this. So we notice that a pretty similar situation happens in cosmological scenario. This famous paper, inflationary spacetime, are incomplete in past direction by Border and Guth and Lincoln. So they are in this work, they are able to show that the inflationary spacetime is past incomplete and circumvent all of the discussion about the energy condition. So basically, it's that the inflationary scenario is past incomplete because any test particle, massive or massless, can be infinitely blue shifted within the, okay, so for massive particle is within its finite property time. Okay, so their result can be also applied to cosmological cycling model with average Hubble expansion rate greater than 0. So this is a model recently promoted by Ijesh and Stanhart. Okay, so then because this idea, we want to see that if we are able to gain some new information or the result based on this geodesic analysis. So, okay, so if we want to, based on the first junction condition, we have to connect the two black hole and white hole smoothly. So this actually implies that the geodesic also have to cross the thin shield smoothly. So this is what we call the no cusp condition. So because this is Schwarzschild solution, so we know the radial geodesic, the full velocity of the radial geodesic. We know the exact form of them. So it can be it's just simply written in this way. And the E is the energy density of the test particle, and R is for bounded geodesic. The R is the maximum radius reached by those particles. So we want to connect the geodesic solution smoothly. So, but notice that we are using a different coordinate system, so we have to find a coordinate independent way to formulate this condition. So this is why we use this gamma, the inner product of the two fold velocities. So one of the fold velocity we choose is this special trajectory. It's actually belong to a radial geodesic. So this is actually those geodesics always stay inside the interior of the black hole and white hole. They never go outside of the event horizon, even through the white hole process. So we choose, so we formulate the no cusp condition in this way. And then by simple calculation, we can get this conclusion. This is what we call the energy shift result. So in order to connect the geodesic smoothly, so the energy changed for the test particle for the geodesic. So what does this mean? Remember, for bounded state, those E is related to the maximal radius reached by the geodesic. And here we just simplify this F vector because usually, because in the usual discussion, the B is very small. So compared to the so we can simplify to this form. So easier algebraically. So from this algebraic equation, probably you need to do some back of envelope calculation, and you can have this conclusion that in this sense, the bounded time-like geodesic become closer to the event horizon in a mass decreasing direction. So the come closer means that the maximal radius reduce after each cycle. Then what? So what then? Because remember the model we consider is actually this kind of cyclic model. There are infinite many of the cycle in this type of model. So if we consider that the mass is always decreasing in one direction, this actually we can show that by a given finite number of cycle, all of the bounded geodesic in one state, they will be all squeezed inside the range of the stretch horizon. This means that when they go out of the black hole and go out of the white hole, they cannot away from the event horizon more than 1 Planck length. So and we can also show that this always happens very early before the system, the black hole and white hole, the mass is still very massive. This means that around the region of the event horizon, everything should be classical. So for example, we can use the solar mass at one stage and until that all of the bounded states are squeezed inside a stretch horizon, the system still has this mass. So it's still pretty heavy. So this is a very weird phenomena. So, and I found this quote in this paper. Gadang can experiment involve black hole. Then there is a quote from Praskill. Apparent contradiction can always be traced to unsubstantiated assumptions about physics at or beyond the Planck scale. So there must be something weird should happen. So the one we think of is still follow this gamma vector. So on the left-hand side is the usual in and out situation. So this is what we think is a usual geodesic. So this time we choose one of the fold velocity is the fold velocity of the pink line here is the in and out geodesic, fold velocity of the in and out geodesic. And the other one is just a usual infalling fold velocity. So if we do this calculation to calculate this gamma vector, the green arrow here means that the calculation, the number is is some like a finite number fairly fall into some reasonable range. And this one is problematic because this is right at the event horizon of the white hole. So this calculation actually explode at this place. But it is okay because how do we find a physical reasonable trajectory able to move in this way and fall into a black hole or move away to the future infinity? So this type is okay, but in this so the problematic here is that the trajectory to have this full velocity, they are also itself is bad. But the situation here is that whenever the infalling object meet this type of a geodesic, all of this calculation, the gamma factor is always very close. So gamma factor is very large. This means that the relative velocity between the geodesic and this infalling object approach to speed of light. And here, because this is the Planck scale difference between the black hole system and the Planck length, so it's the Planck mass. So the difference is the of order of the black hole and the Planck mass difference. So this means that the interaction must be very strong, indicate the instability of this kind of space-time structure. So lastly, so possible rescue and discussion. So in BNN model, they actually propose those two value exchange every time perfectly symmetrically. So this is able to once increase and relax second time. But we think that they are able to construct the picture, the classical picture in this way, but there is no really any dynamical reason why one should follow the other. The second type of picture can avoid this type of problem is also from Donghan's paper, one of Donghan's paper collaborate with Brahma and Chen, is instead of have an infinite cyclic model, we have a time moving point to the different opposite direction. So there is no cyclic picture, but just actually we are placing the two black holes together. Okay, a summary. So in a black hole to white hole bouncing scenario with the mass difference, we find that the radial geodesic lose energy and become closer to the event horizon in the mass decreasing direction. And then by tracing a finite amount of bouncing cycle, all of the bounded geodesic can be squeezed within the range of the stretch horizon, and while the system still very massive. So, and we point out that this type of geodesic are problematic since the unusual infalling object has a relative velocity approach to speed of light for them. So this result should indicate the instability of this type of bouncing model. Thank you. Okay. So the bouncing actually is just inside of the based on the loop quantum gravity construction. The black hole, the singularity is R equal to 0 singularity point is removed and replaced by a transition surface and connected to a white hole face. So there is no equal to 0 singularity at all, because And the idea is that the loop quantum gravity correction modifies the Lagrangian and Hamiltonian, and those can treat it as a semi-classically. So we still have a effective classical space-time model, but just remove the R equal to 0 singularity point. Yeah. So, and this transition, so basically it's this type of transition from a black hole to white hole is called black hole to white hole bouncing scenario. Yeah. Yeah. So.
And thanks again.
Sure.